Again, my name is Jessica Falcone with TDT. I'm a technical sales specialist. I'll be doing the presentation today. I also have my colleague, Victor Rush, on the line. He'll be moderating and fielding your questions at the end of the presentation. Just a little bit of background about myself. I have my PhD in neural engineering from Georgia Tech. For my PhD thesis, I studied brain electrodes, and we were trying to modulate the immune response to extend chronic recordings. And then I did a brief postdoc where I was working on electrodes for the vagus nerve in a mouse model. And then I joined over with TDT, so I've been here for a year and a little bit, and I'm excited to talk to you today about fiber photometry. And also, I just, again, want to say I hope everyone's staying safe and healthy, and thanks for taking time out of our disrupted schedules to move forward and learn a little bit more about fiber photometry today. So very quickly, I'm just going to give you an outline of the presentation. I will be running through an introduction of fiber photometry, and then the presentation is broken into two parts. We'll go over the hardware for the RZ10X. We'll discuss some of the new integration pieces of the hardware, as well as how to set up the new system. And then we'll jump into the Synapse software, which is used to control the RZ10X, and we'll go over some of the new features that we've added in order to make a more simplified fiber photometry experience. And then finally, I'll open up the floor for questions. So feel free to type them into the chat box, and we'll just have some available time at the end to answer those questions. So fiber photometry is a convenient toolkit for neuroscientists. Just so everyone's on the same page, I'm just going to provide a very generic definition. With fiber photometry, you're able to record neural responses using light. You get a population-based response with this technique. And what's really handy is that thanks to the advancements of genetic models, you are able to target specific neural circuits, neural populations in your recordings, and really be able to pull apart your specific and delve into your specific research questions. So for a typical setup for fiber photometry, I usually have one light source, which is recording your signal of interest. So that might be recording calcium using the GCAMP protein or dopamine using delight. And this light source is typically about has a 465 nanometer wavelength. Another light you may record from would be for your motion artifact. So with this, you're going to be recording autofluorescence of the brain, and that light source is typically 450 nanometers. So for the RZ10X, for our fiber photometry, we understand that these experiments that you're conducting are typically in free-moving, behaving animals, and you're trying to integrate fiber photometry and behavior data, as well as potentially other biological signals, and have it all in one place and have it easy to view. And so that was our overall goal with developing the RZ10X, was to create a single system that would encompass all of this data, have it all synchronized in one place, and most importantly, be easy to use. And so this is the RZ10X. And like I said, our main goal here was to have a simplified setup for fiber photometry. So some of the things that we've changed and added on with the RZ10X from our previous fiber photometry system is integrated optics. You can see we've got our LUX optics, or our LUX LEDs and such, which I'll go to in more detail. And then in turn, with our software, as we've further integrated, we've been able to make our software smarter, able to communicate with everything, and have added additional features just to improve the fidelity of the signals in your fiber photometry data. So with the RZ10X, you are able to record from 2 sites or subjects simultaneously, and you can record up to 2 fluorophores per site. So just to show you how the whole system is connected, here are our LEDs, and these would hook up to your optical filter. And so the light will flow into the optical filter, and then with a fiber optic cable, you would connect up to your subject. So your excitation light will interact with your subject, and your emission light will be recorded. And that in turn will go back to your photo sensor. So that's the overall flow of how everything would be connected with the system. So what's in the box? First and foremost, we have integrated an LED driver, and we have specifically designed this to be low power. I will get to the importance of that later in the presentation, so just make a note that our LED drivers are low power. Next, we have integrated LEDs. So as I mentioned, you can record from 2 sites or subjects. So think of each row is for a single site. So in this example, we have a 405 LED for your motion artifact, a 465 for your G-Camp or your D-Light, and then a 560. And that could be additionally added on if you wanted to do any art camp recording. So there's a third LED slot that allows you that flexibility. And then the second row can be populated according to your research needs. Now the next section over here are our photo sensors. So we can have up to 4 photo sensors connected. And in this panel too, since this is our analog input, we also have our power meter. I'm going to explain in greater detail the power meter at a later point in the presentation, so we'll just pause on that explanation for the moment. And then finally, for any slots that are not occupied, we'll simply populate them with a BNC connection or an MA8 driver, so you have access to these channels just as standard analog outputs and analog inputs, so you have the ability to access that as well. So for the LUX LEDs, this is a selection of the different wavelengths that you can select for your RZ10X. And something to really take away from this is that the LUX LEDs are interchangeable. There's just 2 screws connecting them. So if you want to change up your configuration, maybe you only want to start recording from one animal, add on a second one at a later date, you have that ability. And so just with the additional LEDs, you just need to remove the screws, plop in the new LUX LED, and then put the screws back in, and you're able to change up your configuration. Something else of note is since we offer a range of colors, with the system you aren't just tied to just doing fiber photometry, you can also do optogenetic stimulation. So if there's a specific setup that you have for testing out exploring your neural circuit, we are able to modify, and we can provide LUX LEDs in order to do that. So next, for going back to the RZ10X, other things that we can integrate include behavior. So if you have an operant box for your behavior system, we have a DB25 connection with 24 bits of digital I/O, so you can hook up from your operant box, you can connect to our digital I/O. We also have 4 individual BNC connections, each a single bit. So if you just have a BNC cable that you want to connect your operant chamber to the RZ10X, you can do that as well. And the important thing here is now that all of your timestamps or your TTL triggers will now be synchronized with your fiber photometry data, and you'll be able to see all of that recorded in the Synapse software. So all of the data will be synchronized and in one place. We can also incorporate electrophysiology. So the RZ10X has the ability to record up to 32 channels of single units, local field potentials, EEGs, or other biological data. It just requires the addition of an amplifier. And so here are the ports where those amplifiers would connect up to. And again, all the recordings would be done through Synapse, and all of it would be synchronized with your fiber photometry data. Finally, a key feature that we had in our original fiber photometry system has rolled over to the RZ10X. We have real-time walk-in amplification. So how does this benefit you? When you're performing fiber photometry, multiple LED light sources are going to be combined onto a single fiber optic that will be interfacing with your animal. What locked-in amplification does is you have a single raw data stream coming back, and you need to separate out your signals of interest, and lock-in amplification is able to do that. So how it works, Initially, you have your LEDs, and you will be turning them on in a sine wave, which you will be modulating to a specific frequency. And you'll choose a unique frequency for your E1, your first light source, and your second light source. Then you will excite your tissue, so your E1 and E2, your excitation light, will be shined onto your tissue, and the emission responses will be recorded, which is F1 and F2. However, when that data is going back to the photosensor, it's all a single data stream. So your F1 and F2 responses are all mixed in with the additional noise of the system. But using lock-in amplification, which is already coded into the RZ10X, we are able to take that frequency information that we specified in the very beginning and cleanly pull out our signals of interest. And so the big takeaway here is this is something that we've already coded into the signal processor. It's on the back end. You do not have to touch any of it. And so you're able to easily view your GCamp signal in real time, separated out from your motion artifact. And you don't have to worry about any additional coding or figuring out how to make it work. This is something that's already included with the RZ10X and ready to go. And then I just wanted to circle back because we have been making fiber photometry systems for a couple of years. This is our previous system, the RZ5P. And just to give you a comparison of how things have changed between this and the new RZ10X. So to perform fiber photometry previously, for the RZ5P, you would have to hook up your analog outputs to all of these components would be third party. So you would hook up to an LED driver, which would hook up to your LEDs, connect to your optical filter, and then your information would come, your light information would come to your photo receiver, and that would connect back to your analog output of the RZ5P. What we have done is integrated most of these components into the RZ10X. So now, this is what a complete system looks like. The only additional component you need is the optical filter. And then, of course, the fiber optic cables to connect all of the LUX components to the filter and then to connect to your animal. So to summarize, with the new RZ10X, you can now record from 2 sites with up to 2 fluorophores simultaneously. We have integrated LUX components, which includes LED drivers, LEDs, photosensors, and a power meter. You have a whole range of LEDs that you can select from, and these LEDs are interchangeable, so you can reconfigure your system whenever you wish. You still have lock-in amplification for viewing your fluorophore responses in real time. And then we can incorporate behavior and electrophysiology. So just keeping all of your data easily in one place and synchronized. So with that, that concludes our hardware section going over the RZ10X. Now we'll be moving on to the Synapse software, which is what's used to control the RZ10X. And we'll be discussing the new features that we've added in. So from our existing fiber photometry, we have kept some key features. The first being an easy experiment setup with our fiber photometry gizmo. Just think drag and drop and enter in your variables and you're ready to record. So we've kept that easy to use interface. As I mentioned, we have real-time lock-in amplification, which you can see here. You have this data set here is the 465, so I believe that this is D-Light in this real-time example, and then you have your 405, your motion artifact. So those have all been separated out in real time. We still have a video incorporated, so you can add up to 2 USB cameras to record your animals. So that example is shown in this panel over here. And then we have synchronized TTL triggers. So that's for your behavior responses. You can have that all synchronized in with your fiber photometry as well and see that in real time. We have also added in some new features, which I'm going to go into more detail sequentially. So first, we have added an Autodetect for our hardware configuration. You can now view your normalized neural responses, which means you can see delta F over F plots in real time. We also have some automatic timing controls for the LEDs, and I'm then going to go into more detail about the power meter, which we're really using so that you can better standardize your recordings and produce better fiber photometry. So first, we have added Autodetect hardware, Autodetect, so you can see your hardware setup. So the overall goal of this is just detect, connect, and go. With the detect hardware button, automatically populated will be all of the LEDs that are physically connected to the RZ10X. It will tell you what wavelength it is, what channel it's connected to. You'll also see for the analog inputs, you'll see your photosensors, your power meter. All of the banks will be populated and corresponding directly to your hardware. And the whole goal here is that you should just be able to look in the software to see your setup. And the big benefit here is the previous versions, since all the LEDs were external, you would have to manually go through and trace your wires. So, is channel 1 connected up to my 405 light source, and go and make sure that's all happening. So in this case, it's just a button click, everything's connected. You know where everything is located. And this will also help for keeping track of your settings. So you have multiple users using the same system who are going to need to configure things differently, so you can easily see what all is connected and revert back to previous settings so that you can complete your experiments. Next, you're now able to view normalized neural responses in real time. So we have added in a delta F over F plot that can be calculated. So the example shown here, we have the 465 for D light that is being recorded, and then the 405. And then down here, this third data trace is a delta F over F that's being calculated in real time. We use a sliding average window to calculate, and I've provided the equation over here as well. And the big benefit here is you can see your data while you are recording. You don't have to wait to do your offline analysis to know if you are potentially having an effect with your experiment. And then another feature we've added on is you can also remove motion artifact in real time with your delta F over F, and I've provided that equation as well. So again, if your experiment, if your G-camp or D-light is highly affected by motion, you can go and add that calculation into your delta F over F and see a more normalized and clean version of your data. And again, see what the actual neural response is. Next, we've added in some LED timing controls. This first is for in vivo recordings, automatically being able to turn on and off LEDs while you were recording. So the target experiment for this is if you're doing a very long-term experiment, say 6+ hours, and you don't want to keep the LEDs on for that entire period of time because you're worried about accidentally photo bleaching your fluorophores. So with the timing controls, you can set up a paradigm. So say you want to record for 10 minutes every hour on the hour, you can easily set up that paradigm so that your recording will turn off, and then at the start of every hour, it will turn on and record for the prerequisite 10 minutes and then turn off, and have that automatically running while you are doing your experiment. And again, the whole goal of this is just to minimize accidental bleaching of your fluorophore during your in vivo experiments. Next, we have also added in a photo bleaching timer. So this is for on the bench before you start your experiment. And with what we've seen with fiber optics is they inherently have autofluorescence. And if this autofluorescence is not minimized, you're inherently increasing the noise of your signal. So by photo bleaching your fiber optics, you can reduce that autofluorescence and improve your signal to noise. So with this timer setting in Synapse, you can program, you can set how many hours you want to turn your LEDs on for photo bleaching. You can specify your current, select which lights you would like to use for photo bleaching, hit the start button, and then you've got a timer that's running. And the nice thing about this is once the 8 hours have elapsed, the lights will turn off and your photo bleaching is done. Now, finally, last but not least, I want to talk about the power meter, which you can use to standardize your recordings. So why a power meter? I just want to quickly circle back to what I mentioned earlier in the presentation, is that the RZ10X has been designed to be a low power fiber photometry system. So contrary, the opposite of optogenetic stimulation, fiber photometry does not require a lot of power to successfully record. And by using a low power setup, there's a lot of benefits. The first is that by reducing your power, you're going to reduce accidental fluorofluor bleaching. So you'll improve the robustness of your in vivo model. And the second is on the hardware side. We've seen that at low powers, LEDs perform linearly. So that means when you're controlling your fiber photometry, you'll have a more robust signal for collecting your fiber photometry data. So in designing this low power feature into the RZ10X, it became apparent that we needed a way to measure and optimize power output. So that's how the integrated power meter came to be. And from all of this, the main benefits of the power meter is it's a tool so that you can simplify your system setup and debugging. And then further than that, you can use it to minimize your recording variability in between sessions. We've added in quantifiable metrics so that you can have a better idea of your signal quality. And I will go and explain those in the next slide. So this is the example of what you would see in the Synapse software for controlling your power meter, or measuring from your power meter, excuse me. So your first metric is going to be your power output. So this is measured in microwatts. So this is going to tell you how much power you're receiving throughout your entire system, optical filter and all. And then in real time, you can go and adjust your power level by adjusting the current level that is driving your LEDs. So you can specify what power thresholds you would like, say like 10 microwatts. And then over here, you have a bar that will change based on your current. And with the green zone, you have an idea that's a plus or minus range around the 10 microwatts, so you know what target you need to hit, and this number will update, and you can easily adjust your power output in real time. And then taking this further, after you've settled on a power number that you prefer for your experiment, say it's 10 microwatts, you can now go and periodically check and make sure that your system is still outputting 10 microwatts during your recording. So every week, every couple of weeks, go in and check and just make sure it's still working. Next, the next variable we have is transmission efficiency. So this is telling you how much light is retained in your system. So there is a lot of light lost as you're through the connectors, as you're leaving the LEDs, going to your optical filter, and so on and so forth. And so this number is telling you how much of that light is actually retained. So in this example, 21% of that light is retained. So again, you can use this as a debugging tool. So say you plug in and this TX percentage has gone down to 0. All right, that means something, potentially one of the cables are broken. So now you can go and connect the LED. With each cable, you can connect directly to the power meter, go through and say, oh, cable 2 is giving me 0%, it's broken, time to change that out, and just easily go through and debug it. And the same thing with the power. You can periodically attach to the power meter and say, all right, 21% is what I had last week. Do I still have 21%? All right, very good. The system is performing the same as expected. The final variable is distortion. So with distortion, this is related to your DC offset. So as we mentioned, this is a low power system, so we're able to drive, the DC offset is the current needed to turn on your LED. And we are able to drive this very low, down to a couple milliamps. But what we've noticed is in driving your DC offset very low, sometimes you can start clipping your signal. So here's an example of the LED, the sine wave that your LED is generating, and if your DC offset is too low, you end up clipping the signal, and this in turn is going to have an adverse effect on your locked-in amplification and compromise the signal integrity of your fiber photometry. So if this Q percentage dips below a certain amount and the signal starts to clip, it will turn red, and so you know, all right, I just need to turn up my DC offset a little bit, and that way you know that your fiber photometry system is performing optimally. So finally, this is what all your recording is going to look like in Synapse if this is like a real-time animal recording. Very quickly, the first data trace up here is TTL triggers. So you can see that intersecting with the fiber photometry data. We then have 465 for a D-light recording that happened live in vivo, the 405 for the motion artifact, and then the delta F over F trace that was being calculated in real time as well. And you can see that updating with the other fiber photometry components as the data is being collected. So in summary, with the Synapse software, the new features that we've added for controlling your RZ10X, we have the Autodetect feature so that you can view your hardware setup in the software with the idea of detect, connect, and go. We have added real-time viewing of real-time neural responses, so you can see delta F over F and view your data live as opposed to waiting till you do your offline analysis to see if there's an effect. We have automatic LED timing controls. You can control the LEDs for long-term recordings, turning them on and off, and you now have a timer for photo bleaching. And then finally, we have added in the power meter for standardized recordings, and the whole idea here is just for having access to convenient metrics to confirm your signal quality and overall improve the quality of your fiber photometry recordings. So last, I do want to mention that at TDT, we have a team of engineers on the tech support team. They are available by phone, over the internet to help and assist you, whether it's setting up your system, debugging, wanting to start a new experiment. They can also help you with exporting your data. For fiber photometry, online they've posted some great examples of data analysis in MATLAB, so that code is all readily available online. You can take it to start with your initial data analysis or go, modulate it and improve it for your own analysis needs, but all of that's available for you. And then I've listed their email, support@tdt.com, as well as how you can access them on our website. And finally, with the TDT hardware, it all comes with a 5-year warranty, so just a little extra guarantee and insurance when you're purchasing a new system. So with that, I would like to thank you for your attention. Again, my name is Jessica Falcone. I'm on the sales team. If you have any questions, we'll open up the session now for questions, but also feel free to email me if you're interested in more information, you would like to have a Synapse software demo, or you'd be interested in a quote. We are also able to upgrade current RZ5Ps, so that is an option too if that's something you're interested in. And then I just wanted to list the names of our additional sales staff, who I'm sure many of you have interacted with in the past. We've got Victor Rush, April Hatfield, and Beth Smith. So with that, I want to say thank you very much for your time and attention, and let's open up the floor to questions.
Hi, Jessica.
Yes.
We have a question about the photo bleaching.
Yes.
And so if you looked as, here we go, how frequently does the fiber bleaching need to occur? That's from Abigail.
Okay. I do not have a specific answer for this. We are doing some tests. I need to see if that data has been made available. But I do believe from the Doric and Thor labs, they suggest, I think I remember seeing a chart where it was the autofluorescence returned about a week or so after initial photo bleaching. Again, like I said, we're going to go and do, we're going to take a look and confirm those numbers as well. But I would say within a week or so, the baseline autofluorescence does start to return.
And so Mia Anderson wanted to know if the time on the pre-bleaching allowed for control of both the onset and the offset. And
the timing on the pre-bleaching controlled for the onset and the offset. I'm a little of the LED. So the photo bleaching is separate from the timing control. And I'll just go back to this one. For the timing control for the LEDs during recordings, you can add in a delay if that's what you were aiming for your question. So if you want to start your recording but wait 10 minutes until you turn on the LEDs, that is an option as well. And then yeah, everything else is just when do you want to turn on the LEDs, turn them off, and how often do you want to repeat it? Hopefully that answered the question. Let me know if it needs clarification.
And Jeremy Boringer asked, do I need multiple filter cubes from multiple brain regions or animals, or can I do it from one filter cube?
Yes, you need a filter cube for every site or subject. It needs its own filter cube.
And we have a question about whether it works with Synapse Lite from Zipping U.
No, it doesn't. Unfortunately, Synapse Lite is our free version of the software, and that can only control our lab rat. You would need regular Synapse software, but if you purchase the RZ10X, that software is automatically included with the system. So that's all one and the same there.
And Sam Golden said, are there specific patch cables that need to be purchased for the system?
Yes, and I actually do have a slide on that, which we will jump down to. So again, in designing this system, we've been able to go and optimize what cables best connect to which element. So when you're connecting, and we provide a cable kit, which we can add on to the quote. They're available for 2 or 3 LED setups. So all this has already been thought out and put together, so you don't have to worry about this part. But just really quickly, just to show some of the logic in what we were trying to do here, when you're connecting the LEDs to the optical filter, we use a small diameter cable, so 200 micron core, and the whole object here is just to minimize the amount of, while we are a low power system, there's still more light than needed for your recording. So using a small diameter is going to minimize the amount of light going to your animal, and so reduce your potential for photo bleaching. And then the next item and you would want to have low autofluorescent cables connecting from the optical filter to your animal. And then the final piece is a large diameter cable connecting from your optical filter back to your photo sensor. So this would be 600 microns. And the objective there is to get as much light from the optical filter back into the photo sensor for your data analysis. So that's our logic there for why we've selected that. But yeah, we provide a cable kit so that you can connect everything up to the optical filter.
I'm gonna mispronounce the name. Mara said, is the new Synapse version at all backward compatible with the previous processor generation?
Yes, it is. You can still control an RZ5P with the Synapse software, and we do have a legacy option, so that you would have the old fiber photometry gizmo for controlling your RZ5P.
And Christopher Morrison asked, would the output be similar to existing systems, or will you require new MATLAB scripts?
New MATLAB scripts. Oh yeah, everything, it's going to be the exact same as our previous RZ5P, as far as you'll do, all the recordings will be in Synapse, and then you can choose to export into MATLAB, and that data structure will be, there'll be some changes, but you're still going to have your data streams, your epochs, just like some new things that'll be added on is like now you can add in your delta F over F data stream, but it's still the same setup for your data analysis.
And we have a question about, says the comment at the end of the RZ10X section regarding syncing with behavioral electrophysiology is just accomplished through TTL pulses, or can the RZ10X be used to acquire electrophysiology signals?
Right. So sorry, I kind of smushed those together in the name of space. But so the two separate things. So if you're integrating behavior, we can integrate in the TTL pulses through our digital IO. So that's its own item. And then if you want to perform electrophysiology, we have separate fiber optic ports that connect to our TDT amplifiers. And so you would require one of these amplifiers in order to record your signals. So they're two separate things. TTL triggers are for timestamps. You can access that through the digital IO. And then for ePhys, we have separate amplifiers so that you can connect up and record your signal. And the two I have here, the PZ5 can go up to 32 channels. And then the Medusa 4Z is our lower channel count that would do low impedance recordings, such as EEGs or something of that sort. Are there any other questions?
Yes. Can you describe in more detail how the RZ5P can be upgraded? What is added and what is only available with the RZ10X?
So the main differences, let's see, let me think what's the best way to break down that. So for the RZ, for the upgrade, we can upgrade a previous RZ5P. So pretty much the front panel is going to change completely. And you're going to have the ability now to plug in your LUX LEDs, the LUX photosensors, the power meter. So with that upgrade, we're physically going to be changing the RZ5P processor from, I'll just move on to the example. So this is the RZ5P. So this is what it looks like before with just BNC connections. And so it's going to be changing to the RZ10X. So everything on that front panel is going to be changing. And yeah, just the main differences I had mentioned are the integrated LEDs, photosensors, power meter, and then the ability in the Synapse software to control those things to streamline your experiment. I mean, the biggest addition is really having that power meter. Aside from the integrated optical components, is having the power meter, which you can measure in Synapse, and with those additional, like the transmission efficiency and the distortion and the power output, you have now additional metrics to really optimize and streamline your experiments.
Oh, hold on. We have a couple more questions.
Sure.
We have Eric from University of Washington is interested in knowing, in addition to the timing control, how amenable is the software for integrating an automated trigger control with a separate software.
With a separate software. We would have to talk with you, I think, more specifically about what you're looking to do, just to make sure that we have the right solution. Just generally, so if I go back to the digital IO, so that's not just for behavior, you can send and receive any TTL triggers from this. So that would be my suggestion, but I would have to see if your software, if it has a hardware output where it can send out a physical TTL, we could then connect it to one of these interfaces, and then you can use that to control your recordings in that route.
And then finally, we have, does TDT offer courses to send students to for introducing the system and training purposes?
Yes, we are actually in the process of developing a fiber photometry mini, I guess you could call it a mini conference. Unfortunately, with the current pandemic, that has put a temporary pin in those plans. But once, you know, the situation is stabilized in the United States and we are able to again freely move and get on airplanes and convene, we will definitely start offering workshops for the fiber photometry. And yeah, the plan is just to have about a day or so and have a nice sit down of where you can actually program in the Synapse software and go along while someone is directing and teaching the class, so you can actually get hands-on experience with it.
And we finally have a question about the LED drivers and how powerful they are. You mentioned that they're low power, but you also said they could be used to stimulate optogenetically, and optogenetic stimulation requires a much higher power level. How does TDT do that?
Yes, so they do have a range. So while we have designed them to be low power, that's their minimum threshold. So they do have an upper range where you can get into, well, the low power is on the so a couple of milliamp range. You can also drive it up to thousands of milliamps, I believe. I know we can definitely do 1 milliamp. I need to check and see if we can get up to 2 milliamps. So I apologize for not having that right off the top of my head, but we can certainly. Oh yes,
I hope you don't mind, Jessica, but the LED drivers are very linear, as are the LED sources, and they can go linearly from as low as 1 milliamp, which would be in the microwatts, up to 1 amp, which would be in the milliwatts.
Okay.
So.
Okay, cool. So 1,000 milliamps is the cap there then. All right. Okay, do we have any other questions?
We have a couple of questions about the cost of the hardware and the software, but we can discuss that via quotes over the next couple of days and weeks. So if anybody has any quote requests, please send them to Jessica, and we'll get you out quotes as quickly as possible.
Yeah, and then a lot of the pricing is going to vary based on, you know, what your LUX, your LED setup, and photosensors and things like that. And then, yeah, I will be at the end of the webinar, there will be a follow-up email that's sent out, and there will be just a brief survey. It's 3 questions. It's just entitled, did you find this useful? 0 to 10. Any comments, questions, you know, things that we could have improved on, what went well. And then the final is just a yes or no box for whether or not you'd be interested in a follow-up email from us and a quote. So if you could fill that out, I'd appreciate it.
Oh, there's one more question I think I forgot, which is, can you describe in more detail how the RZ5P can be upgraded and what is added and what is only available with the RZ10X?
Oh wait, no, I think we already answered.
We did that one. Okay, good.
So we are good.
Okay.
All right. Well, with that, I want to thank everyone for your attention. Yeah, and taking the time out to learn. Hopefully this was useful for you. And as we mentioned, feel free to reach out to either me or our sales team at sales@tdt.com. And we are happy to take your questions or set up an individual demo with you. So with that, thank you very much. Please stay safe and healthy. And we look forward to interacting with you in the near future. Have a good day.